Hi everyone. So good evening all. So first of all, let me know whether audio and video everything is clear or not. So Uday Kiran, good evening dear. Sri, good evening Sri. Okay. So first of all, let me know whether audio and video everything is clear or not. So if you confirm audio and video, then we can proceed. Right. So is audio and video everything is clear? Yes. Okay. Okay. So it is clear. Right. So in this lecture we are going to study about circulation, curl and Stokes theorem. So mainly we are going to concentrate on the problems here, how to solve the problems based on this, right? Okay. And this is lecture number 8 here. In this series, this is lecture number 8. Okay. Okay. Here. So have you done the problems which I have given yesterday here? Yesterday I have given homework problems. Have you done that one? Have you done the homework problems? So these are the problems I have given. So this one I have given as homework problem yesterday, and the next one. So this is also I have given as a homework problem. Have you done these two problems here? Done? Okay, very good. Yes. Okay. So I think there is no need for me to do. So how much, Uday Kiran, you are getting? 35 pi. No, I think 35 pi is wrong, I think so. Okay. Okay, let us check here. What is there? We can check that. Okay. Okay. So from divergence theorem, we know that I can represent this as triple integral divergence of d bar into what? Into dv. Here we are using cylindrical coordinate system. So the variables are nothing but rho, phi and z, right? And rho is varying from 0 to 1 and phi is varying from 0 to 2 pi and z is varying from 0 to 5, right? And here in cylindrical coordinate system, dv is nothing but what? dv is nothing but just multiply all the three differential lengths here in cylindrical coordinate system. What you are going to get? Rho, d phi, dz. Yes or no? Okay. So rho, d phi, dz. So this is what you are going to get, the differential volume. Now you have to determine this divergence of d in cylindrical coordinate system. So how to express a divergence in cylindrical coordinate system here? So we know that that is nothing but 1 by h1 h2 h3 into what? Into dou by dou u1 h2 h3 h2 h3. So here you can name these components. So this component is nothing but rho component, that is d rho, and this component is nothing but z component, that is dz. Okay. So h2 h3 into d rho. Right. Next one. So it is not going to have any phi component here. Here u1 is nothing but what? u1 is nothing but rho here. u1 is nothing but rho, right? So this u1 is nothing but rho, and h1 in cylindrical coordinate system, h1 is nothing but 1, h2 is nothing but rho, and h3 is also 1. Right. See, always write in cylindrical coordinate system, always write this differential lengths here. What are the differential lengths? D rho, d phi, dz. Right. So the coefficient of d rho is 1. So this is h1. The coefficient of d phi is h2. The coefficient of dz is h3. That's it. Okay. Okay. So here d rho is nothing but d rho So d rho is nothing but 2 rho square aero cap. So this is rho term here. This is rho term, right? Next, you are not having any phi component. Okay, so there is no need to write dou by dou u2. So next you are having z component. So you can write simply dou by dou u3. So here u3 is nothing but what? U3 is nothing but z. So here you have to write h1 h2 into what? Into dz. So that's it here. This is enough. Okay, just substitute the values here. That's it. So here h2 is rho, h3 is 1, and here d rho is nothing but 2 rho square, and here h1 is 1 and h2 is rho, and dz is nothing but z. So just substitute these things. That's it. Okay, so what you are going to get? So here you are going to get 1 by rho into, so here you have to differentiate with respect to rho here. So here what you are having? Here you are having rho, here 1 and here 2 rho square. So that means here you are going to get 2 rho cube. So what is the differentiation of 2 rho cube here with rho? What is the differentiation of 2 rho cube with rho? So that is dou by dou rho into what? Into 2 rho cube plus what? What you are having? Dou by dou z into rho z. So this is what you are having. Okay? Okay. So this is equal to, so 1 by rho, so differentiation of 2 rho cube with respect to rho is nothing but 6 rho square plus what? 6 rho square plus, okay, 6 rho square plus rho into what? Rho into 1, rho into 1. Okay, so here rho, here 1 rho will get cancelled. So finally divergence of d bar, you are going to get simply 6 rho plus 1, 6 rho plus 1. Okay, now just substitute this divergence of d bar in this expression here, in this expression. So what you are going to get? Just substitute here what you are going to get. So integral rho equal to 0 to 1, and here integral phi equal to 0 to 2 pi, and z is varying from 0 to 5, and this divergence of d bar is nothing but 6 rho plus 1 into what? Into rho d rho d phi dz. d phi dz. Okay, see, you can integrate directly with d phi here. So integral d phi is nothing but phi, its range is from 0 to 2 pi, and integral dz is nothing but z, its range is from 0 to 5. Next, what is left out here? Integral rho equal to 0 to 1, 6 rho square. So I am multiplying with rho here. So you are getting 6 rho square plus rho into what? Into d rho. So just to do this integration, that's it. Okay, okay, just I am solving this integration here, right? So I hope it is clear. So if you substitute the range, you are going to get here 2 pi and here 5 and 6 rho square d rho. What is the integration of 6 rho square here? So that is nothing but 6 rho cube by 3. Its range is from 0 to 1, right? Next, plus integral rho d rho, so that is rho square by 2. Its range is from 0 to 1. Okay, so substitute these things here. What you are going to get? So here 2 pi and here 5 and here, so here 3 1s and here 3 2s. So you can write 2 into 1 cube minus 0 cube, that is 1, plus here you are going to get 1 by 2, 1 by 2. Okay, okay. So here 2 pi into 5 into 4 plus 1, that is 5 by 2. Oh, something we have missed here, something we have missed. Is this correct here? Tell me. So here 2 will get cancelled, and here you are going to get 25 pi r. Here you are getting 25 pi. Okay. Okay, Kiran, no problem here. So what is 25 pi r? So you are going to get 78.53 or something. Okay. So this is the value you have to get, right? Yes. So everybody got this value here? 25 pi. Is this clear? Tell me here, Uday, Kiran. Datta, not clear, sir. Okay. Datta, I hope you have attended. This is first class for you, I think so. Okay. So this problem I have given as homework in the yesterday's session, so that I am just revising those things. That's it, right? Okay. So maybe you have attended today, right? So that's why maybe you are not getting. Okay. So if you want to understand everything, you have to attend regularly here. Otherwise, I am helpless, right? Okay. Okay. So you are going to get 25 pi, right? Okay. So next question here. So this question I have given as homework. Okay. So here I have given the current density in a medium is given by Z bar is equal to what? Z bar is equal to 400 sin theta by 2 pi into r square plus 4 AR cap ampere per meter square. Right. The total current and the average current density flowing through the portion of the spherical surface are equal to what? That spherical surface is defined by the portion of the spherical surface. Portion of the spherical surface is defined by r equal to 0.8 and theta is varying from pi by 12 to pi by 4 and phi is varying from 0 to 2 pi. Right. So they are asking what here? They are asking the total current that is flowing through the surface, that is flowing through the portion of the spherical surface that is defined by these parameters. Right. Okay. So they are asking I total, and also they are asking what? They are asking the average current density. Right. Okay. Okay. So if you observe here, what is the portion of the spherical? What is the portion of the sphere they have given here? See here. Let us consider this as z-axis, and this is x-axis, and this is y-axis, right? So this is z-axis, and this is x-axis, this is y-axis, and this is z-axis, right? Okay. Okay. So here theta is varying from pi by 12 to pi by 4 and r value is what? 0.8 meters. So r value is 0.8. So the distance from the center, let us take. Okay. So let us consider this is r equal to what? R equal to 0.8 meters, right? And the angle between z axis and r is nothing but theta, right? So initially the theta value is pi by 12. So here theta is equal to what? Equal to pi by 12. Okay, theta value is pi by 12, and it is varying from pi by 12 to what? Pi by 12 to pi by 4. So let us say at this point, let us say this angle theta equal to pi by 4. This angle is theta equal to pi by 4, and this is r. Okay, so this is the arc here. This is the arc you are going to get. Yes or no? Okay. As theta varies from pi by 12 to pi by 4, so this is the arc you are going to get. Okay. So now phi is varying from where to where? 0 to 2 pi. So that means just rotate this arc here. Just rotate this arc 0 to what? 0 to 2 pi. That means complete one circle like this. Okay. So take the arc here and rotate it by 2 pi degrees. Understood? Okay. Rotate it by 2 pi radians or rotate it by 360 degrees. Understood? So then what you are going to get? You are going to get if you rotate this, you are going to get, something like this, and here, okay. So this is the spherical region you are going to get here. So this is the portion of the spherical region that you are going to get, right. So theta is varying from pi by 12 to pi by 4. So you are going to get one arc like this, and phi is varying from 0 to 2 pi. So that means take this arc and rotate it by 2 pi radians or 360 degrees. So that is the portion, whatever that is covering here. So that is the portion of the sphere. That is the portion of the sphere, right? Okay. That is the portion of the sphere here, right? Okay. So now they are asking the total current that is flowing through the surface of this region. Total current that is flowing through the surface of that region. And here they have given the current density here. Here they have given current density. So what do you mean by current density here? Current density is nothing but the current that is penetrating per unit area. So if you consider a small differential area over this surface, if you consider a small differential area over this surface, so the current that is penetrating, per unit area is nothing but Z bar. Now if I consider a small differential surface on this, if I consider a small differential area on this surface, then what is the current that is going to penetrate over this small differential area dA bar here? Z bar is nothing but the current that is penetrating per unit area. And if I want to determine the current that is penetrating through this small differential area, then what I have to do? So that is nothing but Z bar dot what? Z bar dot dA bar. So this is going to give you the current that is penetrating through this small differential area dA bar. Now if I want the total current that is flowing throughout this surface, then what I have to do? I have to integrate throughout this surface. Understood? So on this surface, what are varying here? Theta is varying and phi is also varying. Yes or no? So if you move along this surface here, R will remain same here. R is remaining same. So what is going to change? Theta is going to change and phi is going to change. Right? See, on the surface of the sphere here, if you move on the surface of the sphere, so the surface of the sphere is defined as what? R equal to constant plane. Yes or no? R equal to constant plane means theta and phi are varying, right? And here they have given a portion of the surface of the sphere. So that means what are the variables on this surface? Theta and phi. Understood? So you have to integrate here with respect to what? With respect to theta and phi. Here the differential area is nothing but what? What is the differential arc length along theta here? The differential arc length along theta is nothing but r d theta. And what is the differential arc length along phi? So that is nothing but r sin theta d phi. And what is the direction of the surface? What is the direction of the surface? If you draw the normal on the surface of the sphere, it always points in which direction? It always points in AR cap direction. Understood? So it is going to point in AR cap direction. Now just substitute here Z bar value and determine this one here. Now here they have given theta is varying from where to where? Theta is varying from pi by 12 to pi by 4, and phi is varying from 0 to 2 pi. Now substitute the value of Z bar, then you are going to get I total. Okay? Okay, yeah. So Gajendra Singh, sir, it's my first class. Okay. So if you are having already idea on these things, then you will understand here. So otherwise, I suggest you to go through the previous lectures. Okay. So if it is a if you continuously go through all the lectures, they are in sequence here. So if you understand those, then you can understand these things easily. Right? Okay. 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 So now here I want to determine this I total. So I total is equal to what? Is equal to double integral Z bar dot dA bar. Right? Here the variables are nothing but theta and phi. Theta is varying from pi by 12 to pi by 4, and phi is varying from 0 to what? 0 to 2 pi. And this dA bar is nothing but what? So this is the small differential area on the surface of the portion of the sphere. So on the surface of the sphere, the variables are nothing but theta and phi. So here this differential area will become r d theta into what? R d theta into R sin theta d phi. So that is, I can write it as R square sin theta d theta d phi AR cap. So this is the small differential area on the surface of the sphere. And here z bar they have given as what here? They have given as 400 sin theta divided by what? Divided by 2 pi into R square plus 4 AR cap. So this is what they have given, right? Okay. So this is z bar and this is dA bar. So perform this integration here. Perform this integration. That's it. Okay. Okay. So what you are going to get here? If you do this, what you are going to get? So theta equal to pi by 12 to pi by 4, and phi is varying from 0 to 2 pi, right? So if you do the dot product between these two, what you are going to get? What you are going to get here? So you are going to get 400 by 2 pi into R square plus 4, and here you are having R square. So next here sin theta, here sin theta. So that is sin square theta d phi, and AR cap dot AR cap will become 1. So this is what you are going to get. Here the integration variables are nothing but theta and phi. So that means R is constant with respect to this integration. So you can take all these R terms outside the integration. So what you are going to get? 400 R square divided by 2 pi into R square plus 4. Okay. Okay. Okay here. So next integral theta equal to pi by 12 to pi by 4. Here you are having what? Sin square d theta. So I am writing here sin square d theta. So what is the integration d phi here? With respect to phi, if you integrate, integration d phi will become phi. Its range is from 0 to 2 pi. That's it. Okay. So now just solve this integration here. So substitute here in place of sin square theta. In place of sin square theta, substitute here 1 minus cos 2 theta by 2. Okay. Okay. So solve this integration here. What you are going to get? What is the value you are going to get? So here 400 R square divided by 2 pi into R square plus 4. Here if you substitute this range, you are going to get this value as 2 pi. So here 2 pi, right? Okay. So here you are having theta equal to pi by 12, 1 minus cos 2 theta by 2 into what? Into d theta. Do this here. Do this. What you are going to get? Tell me. So here 2 pi and here 2 pi will get cancelled. So in place of R value is how much here? 0.8. So in place of R, substitute 0.8. Okay. Okay. So what is the answer you are getting? Tell me. Tell me here. Uday Kiran, Sri. What is the answer you are getting? Tell me. Keep notebook and paper with you, and whenever I am asking you to calculate something, so do it here. Do it and tell me the answer. If you solve this integration, you are going to get 1 by 2 theta 0 to pi by 12 to pi by 4 minus so cos 2 theta is sin 2 theta by 2. Its range is from pi by 12 to pi by 4. Okay. So do this here. Solve this one here. Tell me the answer. What you are getting? 27.58 amperes. Check once, Sri. Check once. I don't think you will get a 27 point something like that. Okay. Check this here. Do the calculation here. Do the calculation. So this value you will get 55.17. Here you are getting 1 by 2. Here this value will be so this value will be 0.523 minus so 2 into pi by 4, that is sin pi by 2 you will get. So 1 minus sin pi by 6, right? Okay. So that is here you will get 1 minus sin pi by 6. So pi by 6 means sin 30. So 1 minus 1 by 2 you will get. Okay. So here this value is 1 by 2. Here 1 by 2, 1 by 4. So 0.523 minus 0.25. So that is 0.273 into 55.17. 15.06. How much you are getting here? $25.71. Maybe while substituting the values here, maybe you are doing you are substituting 2 into pi by 4. See, sine of 2 into pi by 4 is nothing but what? Sine pi by 2, that is 1 minus of what? Pi by 12. If you substitute pi by 12 here, 2 into pi by 12. So 2 into pi by 12 means pi by 6. Sine pi by 6 value is 1 by 2. So 1 minus 1 by 2 value is 1 by 2. So here already 1 by 2 is there. So you are going to get here 1 by 4, right? 1 by 4 you are going to get here. And here you are having 0.523, right? So here this is pi by 4 minus of pi by 4 minus of pi by 12. So that is 0.523. Okay. So 0.523 minus 0.25. So 0.273. 0.273 here you will get divided by what? Divided by 2. So 0.136 into 55.17. So you will get 7.5 something here. So you will get 7.54 amperes. So this is what you have to get here. 0.523 minus 1 by 4, it is approximately 1 by 4. 0.523 minus 1 by 4. Okay, do this one here, do this calculation, 0.523 minus 1 by 4, and then this total thing has to be multiplied by 1 by 2. So then this total thing has to be multiplied by 55.17. So you are going to get 7.54 amperes. Okay, so I think you are doing some calculation mistake. You can check that. You have done some calculation mistake, I think so, right? Uday, Kiran and Sri. Check whether you where you have done the mistake here. Maybe in calculator, maybe you have kept in degrees itself, and you have substituted pi by 4 directly here. So that's why maybe you are getting some wrong answer or something. Okay, okay. So current must be what? 7.54 here, right? Okay, okay. So this total value here, this total value you are going to get 0.1365. Okay, this multiplied by this one is going to be 7.54 amperes. Clear? Tell me here. Confirm Uday, Kiran and Sri. Yes? Okay. So next they are asking the current, average current density, that is J average current density. So average current density is equal to what? Is equal to, so I total divided by what? Divided by the surface area. Yes or no? The total surface area. So they are asking the average current density. On an average, what is the current density that is flowing through this surface? So what you have to do? You have to take the total current divided by what? Divided by this total surface area. So that is going to give you the average current density. Yes or no? Okay. Okay. Yeah. So J average is equal to what? Is equal to I total divided by what? Divided by area. Divided by area. So I total just now we have determined, that is 7.54 amperes. So this is equal to 7.54, and what is the area here? So area is nothing but what? You have to consider the area of this portion here. You have to consider the area of this portion. So what is the area of that portion here? If you want the area of that portion, you have to integrate over this ranges here, over this range. Yes or no? Okay. So what is the area? Tell me, what is the area? So area is nothing but you have to write double integral dA. So here theta is varying from where to where? Theta is varying from pi by 12 to pi by 4, and phi is varying from where to where? 0 to 2 pi. Phi is varying from 0 to 2 pi. And what is this differential area here? So this differential area just now we have seen, that is r square sin theta d phi. Okay. So just to do this one here, you are going to get what? You are going to get the average current density. So that is 7.54 divided by r square is constant with respect to this integration. So take it outside the integration. So you are going to get r square. So next integral d phi is nothing but phi, and substitute the range here. Substitute the range of phi. So what you are going to get? Phi is ranging from 0 to 2 pi. So next what is left out here? Integral sin theta. Integral sin theta is nothing but what? Is nothing but cos theta. Integral sin theta is nothing but cos theta. Its range is from pi by 12 to pi by 4. Okay. So substitute this one here. What you are going to get? Tell me. See, whenever you are calculating here, while doing the calculation, okay, so make sure that if you are substituting directly pi by 4 here, you have to keep it in radians. Understood? So if you convert this into degrees, then you have to keep it in degrees here while calculating through calculator. So that's what you have to be cautious, right? Okay. Okay. So this is equal to 7.54 divided by what? This r value is 0.8 here. So here you are having 0.8 whole square. Here this is 2 pi, and here you are going to get cos pi by 4 minus cos pi by 12. So if you are calculating cos pi by 4 minus cos pi by 2, be cautious that you have to keep it in radians, right? Your calculator must be keep it in radians, right? Okay. Tell me here, tell me the answer, what you are going to get? What you are going to get, tell me. sorry, here what is integration of sin theta here? Integration of sin theta is, I think, minus cos theta here, yes or no? So I forgot to put minus here, okay? So put here minus here, put here minus. So I forgot to put minus here. Integration of sin theta is minus cos theta. Minus cos theta or cos theta here? Integration of sin theta. Okay. So what you are getting here? Tell me. So you will get approximately the same value here. You are going to get approximately 7.54 only, right? You will get approximately 7.54 ampere per meter square. So this is the average current density here. So this total value you are going to get approximately 1 here. Approximately you will get 1, this total value, right? So current density is also what? Current density value is J average is equal to what? Is equal to 7.54 ampere per meter square. So the same value here, approximately you are going to get the same value for I total and average current density, right? Okay. Okay, yeah. Yes. Okay, so with this we have completed the problems based on what? Based on flux and then divergence theorem, right? Okay, so we have solved different types of problems based on flux and divergence theorem, right? Okay, okay. So next here. So next we will see briefly about circulation of vector field, around any closed loop. How to represent the circulation of vector field around any closed loop. Okay. Circulation of vector field around any closed loop, right? Okay. So what do you mean by this here? Circulation of vector field around any closed loop. What do you mean by this? So that means you are determining how much of the given vector field is aligned around the given closed loop. So it is nothing but what? It is a measure of how much of the given vector field, is aligned around a given closed loop. So that's what we mean by circulation of the vector field around any closed loop. Okay, see here, for example, see, if suppose I have given here positive charge plus Q, right? We know that whenever you place a charge here, it is going to set up some electric field in its vicinity, and that electric field will be radially outward. So it is going to produce an electric field, and that field is going to radiate radially away from what? Away from the charge. So this is radially outward. So that means here the field is what? The electric field is in which direction here? It is in AR cap direction. This is radially outward direction, Understood? Okay. Okay, yeah. So now see here, if I try to determine the circulation of this electric field, around this closed loop here, I am considering a circular loop here. For simplicity, I am considering a circular loop here, right? Okay. So this is nothing but circular loop. Okay, now tell me what is the circulation of the electric field around this closed loop. So that means I am asking how much of this given vector field is aligned around this closed loop. How much of this given vector field is aligned around this circular loop? Tell me here. Tell me the answer here. Uday, Kiran, Sri. Tell me here. So Harsha Kumar is absent today, right? Okay. Okay. Uday, Kiran and Sri, tell me. What is the circulation of electric field around this circular loop? That means I am trying to determine how much of this electric field is aligned around this closed loop. That's what I am trying to determine. So what you are going to get? Tell me. See here. If I consider a small arc length here, if I consider a small differential arc length here, right? Okay. So the direction of this arc length is going to point in which direction here? It is going to point in a phi cap direction, right? And here the electric field is pointing in which direction? AR cap direction. Understood? Now I want to determine how much of this electric field is aligned over this small differential length. So let us say this small differential length is dl bar. This small differential length is dl bar. Understood? Okay. So how to determine how much of the given vector field is aligned around the along this arc here? How to determine? So that is nothing but what? E bar dot what? E bar dot dl bar. E bar dot dl bar. Now here E bar is pointing in which direction here? AR cap direction, and this small differential length is pointing in which direction? For any arc, what is the direction here? The direction of arc is given by the tangent drawn to that arc. So if you draw the tangent to this arc, that is going to point in a phi cap direction. Understood? So the differential arc length, it is pointing, this direction is along a phi cap direction, So this is going to give you how much of the given vector field is aligned over a small differential length dl bar. Now if I want to determine how much of this electric field is aligned around this total circular loop, then what I have to do? I have to integrate throughout this circular loop. So that means I have to do closed loop line integration throughout this circular loop. Understood? Now here at each and every point around this circular loop, the direction of electric field is along AR cap direction and the direction of arc length is along A phi cap direction. We know that AR cap direction, that is radial direction, A phi cap direction, that is tangential direction, both must be what? Both are always perpendicular to one another. So this dot product will result in what? This dot product will result in equal to 0. So that means the circulation of the electric field around this closed loop, you are going to get what? You are going to get 0. Yes or no here? So throughout this circular loop, the electric field direction and the loop direction both are perpendicular to one another, and hence there exists no component of electric field around this closed loop, right? So that's why you are going to get the circulation of electric field around this closed loop is equal to 0. So which means no electric field is going to be aligned around this closed loop. The alignment of the electric field around this closed loop is equal to 0, right? Okay. So is this point clear? Tell me. Is this point clear? Is this point clear? Tell me. Uday, Kiran, Sri. Tell me here, is this point clear? So now see here, I will take another example here, I will take another example. And here, if suppose if I take a current carrying wire, I am considering a current carrying wire. Let us say this is the current carrying wire. So it is carrying a current I in this direction, let us assume. Okay. So whenever you are having a current carrying wire carrying the current in this direction, so it is going to set up what? It is going to set up a B field in its vicinity. So that B field is going to circulate around this wire, around this wire. So this is going to form the circular loops like this. Right. So now this is nothing but what? This is nothing but B field. Right. Now if I try to determine the circulation of B field around this closed loop here. So I am considering a closed loop like this. Now I am considering a closed loop like this, right? So this is nothing but loop. This is nothing but loop. Right. Okay. Closed loop. Now here the B field, what is the direction of B field here? The direction of B field is in A phi cap direction, and here the loop also I have considered as what? Circular loop. So the direction of the loop is also in what? Is also in A phi cap direction. So the direction of the B field as well as the direction of the circular loop, both are in what? Both are in the same direction, that is in A phi cap direction. So in this case, if you try to determine the circulation of B field, the circulation of B field around any closed, around this closed loop, what you are going to get? You are going to get not equal to 0. You are going to get not equal to 0. Okay, and from Ampere's law, we know that the circulation of B field around this closed loop is equal to what? Is equal to mu times of what? Mu times of current enclosed. So this is what is called as Ampere's law. Yes or no? So here B field is pointing in A phi cap direction, and the loop direction is also in what? Is also in A phi cap direction. Loop direction is also in A phi cap direction. Understood? So now here you are trying to determine how much of this given B field is aligned around this closed loop. So since the direction of B field as well as the direction of loop both are pointing in the same direction, so whatever the B field that is present here, the total B field is aligned around this closed loop. Right. Okay. So the circulation of the B field, that is how much of the B field that is aligned around this closed loop, is equivalent to what? Is equivalent to mu times of current enclosed by that closed loop. So this is called as what? This is nothing but Ampere's law. This is nothing but Ampere's law. Right. Okay. Okay. Yeah. So that means whenever you are trying to determine the circulation of the vector field around any closed loop, that means you are determining how much of the given vector field is aligned around that closed loop. Right. Okay. Okay. Yeah. So whenever they ask to determine the circulation of the vector field, if suppose they have given some vector field f bar and they ask to determine the circulation of the vector field around some closed loop, then what you have to determine? You have to determine closed loop integral f bar dot what? F bar dot dl bar. So this is going to give you the circulation of vector field around closed loop, around a closed loop. Okay, so this is the mathematical representation of the circulation of vector field around any closed loop. Okay. Okay. Right. Okay. Okay. Next, once you have understood circulation, how to represent the circulation of vector field around any closed loop, so next we will move on to curl here, curl. Okay. So I will just give you brief definition of curl. So curl, it is a measure of what? It is a measure of how much of the given vector field, how much of the given vector field is tending to circulate, about a given point, okay, or I can say simply it is a measure of what? It is a measure of circulation about a given point. So, circulation of vector field about a given point, circulation of vector field about a given point, okay. So, curl, it is a measure of how much of the given vector field is tending to circulate about a given point, or I can say it is simply the circulation of the vector field about a given point, okay. Yeah. So, that means, see here, I will give one example here, If suppose if you are having the vector field like this here, if you are having the vector field like this, so you are having some vector field like this. Now here in this vector field I have placed an object like this, right. Okay, so I have placed some object like this, so in this field, right, okay. So now tell me whether this field is having the circulation about this point or not. Tell me how you can determine whether this field is having the circulation about this point or not. How you can tell? See here, the field strength, as you move from bottom to top, the field strength is increasing. Let us assume it is the velocity flow of water here. Let us assume this is the velocity of water flow or something, okay, velocity. So if you observe here it is having more velocity and here it is having less velocity. So that means this water flow is hitting with the more velocity at the top and it is hitting with the low velocity at the bottom. So then what will happen here? So this object will tend to circulate. In which direction? It tends to circulate in a clockwise direction like this or not? Yes or no here? So that means this field is having what? Is having the circulation about this point. It is having the circulation about this point. Understood? Okay. Now similarly, if I consider the field like this, here, if I consider the field like this, so then, and if I consider the object here, if I consider some object like this, right, in the same manner, okay. So now tell me whether this field is having the circulating nature about this point or not. Tell me whether this field is having the circulating nature about this point or not. Tell me. See here, on this side it is hitting with what? It is hitting with more velocity, and on this side it is hitting with lesser velocity. So this object will tend to circulate in which direction? It tends to circulate in anti-clockwise direction. Yes or no? It tends to circulate in anti-clockwise direction like this. Right. Now if I consider another field here, if I consider another field, like this, okay. So now if I place some object, in this field, okay. Now tell me whether this object will tend to circulate about this point or not? Tell me. Yes. So now tell me, this object will tend to circulate about this point or not? Tell me. The field here, the velocity of the flow is same, is uniform throughout the space, right? So in this case, it is not going to circulate about this point. So you can say the curl at this point, the curl of the vector field at this point is equal to what? Is equal to 0. So this is what you can say. Okay, so curl is nothing but what here? Curl of any vector field is nothing but what? It is a measure of circulation of the vector field about a given point. Circulation of the vector field about a given point. Understood? So here you can say simply the curl is equal to what? The curl is equal to 0. Right? Okay. So it is not tending to circulate about this given point. So that means the curl of the vector field at this point will be equal to what? Will be equal to 0. Right? Okay. Okay. So I have given in-depth analysis of this circulation and curl in the EMT playlist already, which is available in our channel here. Okay. So that's why here I am just briefly giving or explaining with some few examples. That's it. Okay. Okay. So now see here. Mathematically, how we are going to express curl here? Mathematically, we are going to express curl of f bar. Okay. So generally, we are going to express the curl by what? By the determinant form. So in rectangular coordinates, you are going to express it as ax cap, ay cap, az cap, and here dou by dou x, dou by dou y, dou by dou z, and here f bar is having x component as well as what? Y component as well as what? Z component. So here represent x component of vector field, y component of vector field, and z component of vector field. So then you are going to express. These things. Yes or no? Okay. Okay. So instead of following all these things, I will tell you a method how to expand this curl in all the coordinate systems here, whether it is rectangular coordinate system or it is a cylindrical coordinate system or it is a spherical coordinate system. So in all these coordinate systems, how we have to express this curl. So that's what I am going to explain now, right? Okay. Okay. So see here. So for this, first of all, I am going to give you have to write this one here. So that is, in rectangular coordinate system, the coordinates are nothing but what? The coordinates are nothing but x, y, and z. So I am forming a table here. I will give you the table here. So I will tell you how to express this curl in all the coordinate systems, right? Okay. So here u1, u2, u3, these are the coordinates in different coordinate systems. So next here I am writing h1, h2, h3. So these are nothing but coefficients of, in rectangular coordinate system, h1 is coefficient of dx, h2 is coefficient of dy, h3 is coefficient of dz. Right. In cylindrical coordinate system, h1 is coefficient of d rho and h2 is coefficient of d phi, h3 is coefficient of d theta. Sorry, h2 is coefficient of d theta and h3 is coefficient of d phi. Sorry, what I am saying here? Wait. In cylindrical coordinate system, h1 is coefficient of d rho and h2 is coefficient of d phi, h3 is coefficient of dz. Right. In spherical coordinate system, h1 is coefficient of dr and h2 is coefficient of d theta and h3 is coefficient of d phi. Right. Next, here f1, f2, f3. Okay. Okay. So here write down for rectangular and then cylindrical and then spherical. Right. So in rectangular, the coordinates are nothing but x, y, z. And h1 is nothing but 1, h2 is 2, 1, h3 is also 1, f1 is fx, f2 is fy, f3 is what? Fz. Okay. In cylindrical coordinate system here, what are the coordinates here? You are having rho, phi, z. Right. And what is h1, h2, h3 here? Just write down the differential lengths here. Just write down the differential lengths in cylindrical coordinate system. What are the differential lengths? They are nothing but d rho, d phi and dz. So the coefficient of d rho is nothing but what? Is nothing but h1, and the coefficient of d phi is nothing but h2. The coefficient of dz is nothing but h3. Okay. So write down those values. So here h1 is 1, h2 is rho, h3 is 1, right? And here f1 will become rho component, f2 will become phi component, and f3 will become z component. Next, in spherical coordinate system, the coordinates are nothing but r, theta and phi. Okay. Okay. So what is h1, h2, h3 here? So in spherical coordinate system, write down the differential lengths here. So that is dr, r d theta and r sin theta d phi, r sin theta d phi. Okay. So the coefficient of dr is nothing but h1. The coefficient of d theta is nothing but h2. The coefficient of d phi is nothing but what? Is nothing but h3. Okay. So just represent these things here. What you are going to get? So h1 is 1, h2 is r, h3 is r sin theta, and here f1 is r component, f2 is theta component, and f3 is phi component. Okay. Okay. So form your table here. Form your table. Okay. So form this table here, right? So curl of f bar here, curl of f bar is equal to, we can write in this manner, 1 by h1, h2, h3, and here it is h1 au1, h2 au2 cap, h3 au3 cap, and here dou by dou u1, and here dou by dou u2, and here dou by dou u3, and here f1 h1 f1, h2 f2, h3 f3. Okay. So this is the determinant form here. This is the determinant form for the expansion of curl in all the coordinate systems, whether it is rectangular or it is what, or it is cylindrical or it is spherical. So this is the expansion of curl. This is how you have to expand the curl, right? Okay, in determinant form here, in determinant form. Right. Okay. Okay. Note it down here. Note it down. Is this completed? today I think very less number of students are present here on online, right? Very few students are present, and the number of views and number of likes also very less today. Okay. Okay. Okay, so make a note of these things, right? Okay. So today I am going to wind up the session with this, right? So if more number of students will come, so then I can take some more number of hours here, like I can take 1.5 hour or 1 hour 40 minutes, like that. Okay. So if views are very less, means we don't get that motivation to take that much of time, right? Okay. Okay. So anyway, for today I am winding up the session with this. So tomorrow I will explain the Stokes theorem, and also I will tell you how to write this determinant and all those things here, how to expand this determinant, how to write in a simple manner. So those tricks also I am going to discuss in tomorrow's session. Okay. So tomorrow I will discuss how to express this one, how to expand this determinant in a simple way. Okay, that's what I am going to explain, and also I will explain Stokes theorem, right? So based on that Stokes theorem, we try to solve 1 or 2 problems. So if it is completed, then we are going to start conductor's topic here. So if we complete the Stokes theorem, problems on Stokes theorem, then we are going to start conductor's topic, right? Okay. 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 So with this I am winding up the session for today. So tomorrow at 7:30 p.m. See, if more number of students attends the session, okay, so then I can take up to 1 hour 40 minutes or 1 hour 50 minutes, even 2 hours 3 hours also. Okay. But if very less number of students are present, means we can't take more than 1 hour here, right? Okay. Okay. So tomorrow we are going to meet exactly at 7:30 p.m. right? So with this I am winding up the session for today. So we'll meet tomorrow here. So until then, take care. Bye bye.